In this video, we're going to talk about fixing the Bohr model to account better for how atoms actually behave. In the last video, we showed that, or we discussed that Bohr's model worked well for atoms that were basically like hydrogen. In other words, atoms that only had one electron in the electron cloud. But the spectra were off for atoms that had more than one electron. So, it seems the difference is, in the original Bohr model, Bohr was modeling the interaction between the proton and the nucleus and the electron. Now, when you only have one electron, that's all there is. But when you start to have more than one electron, you not only have to look at the interactions between basically the protons and the electrons, but you also have to look at interactions between electrons and other electrons, because opposite charges attract, but like charges repel, and that will affect how the electron cloud is organized. So the issue is, we need something that can handle electron-electron interactions. But there was a problem. Of course, Bohr's model was too simple, his initial model, and attempts to actually fix Bohr's model by trying to model electron-electron interactions ran into a problem. The problem was they modeled electron-electron interactions the same way they modeled electron-proton interactions. But the math never seemed to work out. In other words, what they calculated and what reality was, observed by atomic line spectra and other things, just didn't match. And it basically took essentially a revolution in physics for them to sort this problem out. So one of the things that was discovered about electrons is that electrons are, of course, particles with known masses, but electrons exhibited diffraction just like waves do, light waves, water waves, and so forth. So what they tried to sort out was, okay, well, how can we account for the fact that electrons diffract? Physics had thought of waves and particles as different things in what they call traditional or classical physics. But they had to acknowledge that some things we know of as particles have wave characteristics, and some things we know of as waves, like light, thanks to Einstein, has particle characteristics. So essentially, they had to go from viewing waves and particles as being completely separate things to waves and particles as being two aspects of the same thing. So to fix the Bohr model, you essentially had to redo your physics to treat electrons as if they have wave behavior. Now, I put an equation here called the de Broglie relationship. Now, we're not going to calculate anything with this, but I just want you to look at the form of the equation, because what this equation does is it tells you the wavelength of a particular particle. So, take a look at the form of the equation. In particular, look at where the mass is. The mass is on the bottom. So what this says is, as the mass of the particle goes up, the wavelength, which is essentially the wave behavior, goes down. So when a particle's size gets really large, like, say, tennis balls, human beings, even maybe protons, the wavelength ends up being really, really small. So essentially, the bigger the particle is, the smaller its wavelength is, and the more its wave characteristics can be effectively ignored. So if you're calculating where a human being is going, you can probably ignore their wave behavior. And when Bohr was calculating the behavior of a proton and an electron relative to each other, the wave behavior didn't seem to matter too much. But when you start looking at electrons interacting with electrons, and just electrons specifically, their mass is so small that their wave behavior tends to be very significant. In other words, it's not ignorable anymore. And that's why trying to fix the Bohr model with classical physics never ended up working. So, the new branch of physics that arise from treating things like waves is called quantum mechanics. So what quantum mechanics does is it treats electrons and particles like that as waves do, and it models that wave behavior. To describe the behavior of the electrons, they use wave functions, which are basically essentially complicated equations. We're not going to deal with the math ourselves here in freshman chemistry. What we will do is we will allow the physicists to do what they do best, which is the complicated math, and we will talk about what the wave functions tell us about how the electron cloud is structured. Now, one thing that's a little different about quantum mechanics than traditional physics that you probably learned in high school or in a college freshman physics class is that we talk a lot in classical physics about the location of a particle, the direction it's going, its momentum, all that other stuff. And the wave function is essentially a probability distribution. So the wave function tells you how likely it is that you're going to find a particular particle, in our case an electron, in a given space. So the wave function for an electron describes a region where the electron is. We don't really focus usually that much on a particular position of the electron, just where around the atom is it likely to be. Now, we don't have to deal with this behavior all the time. So for larger objects, the wave behavior basically zeroes out, and quantum mechanics becomes traditional classical physics or Newtonian physics, whichever term you want to apply to it, that you've learned all along. But we deal with electrons, so we have to deal at least with the implications of this quantum theory. Now, when we talk about the electron, we are not going to solve wave functions or anything like that in Chemistry 110, but what we'll do is we'll talk about these things called quantum numbers. So you can think of quantum numbers as kind of the parameters that go into the wave function, or you can think of them kind of like solutions. You know, from math class, you probably learn about higher order equations. You know, linear equations have one solution. Quadratic equations have two solutions, second order. The higher the order of the equation, the more possible solutions it has. Well, quantum mechanics is kind of the same thing. We can think of these parameters or solutions that describe the behavior of the electrons. Now, the original Bohr model only had one parameter. The only thing that mattered in the Bohr model was which energy level you were in. In other words, how far your electron was from the nucleus. That's all the Bohr model talked about. But in quantum mechanics, it's a little bit more complicated, as you might expect. There are four of these parameters that describe the electron. There's the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and then the spin quantum number. These four together essentially identify where an electron is and essentially what its properties are going to be. You can think of the quantum numbers kind of as maybe the phone number of an electron. We have a class, when we're meeting in person, we may have a class of up to 18 or so people, and everybody in there has a phone. And everybody's phone has a unique phone number. Because if a bunch of people had the same phone number, then you'd never know who you got at the other end when you started dialing. So everybody has an individual phone number. But we share some digits, right? I mean, we can all have an 8 in our phone number somewhere. What matters is that we don't share all the digits in our phone number. So the quantum numbers work kind of the same way. In any particular atom, you only have one electron that has a particular set of four of these quantum numbers. Now, some atoms will have the same one, 2, or even 3 of the quantum numbers the same. But every electron in an atom has a unique set of 4 quantum numbers. And those will describe basically what the electron cloud looks like. So let's talk about each one of these in a little bit of detail. First, let's talk about the principal quantum number. Luckily for us, we kind of know that one already, because the principal quantum number, which is given by n, is essentially the same thing as Bohr's energy levels or shells. Now, in the Bohr model, the shell basically represented the distance of the electron from the nucleus. And basically that's all there was. The energy of the electron basically came from how far it was from the nucleus. In quantum mechanics, basically the principal quantum number represents the same thing, the distance of the electron from the nucleus, but it's only part of what contributes to the energy of the electron. So, mostly similar to the Bohr model, but some slight differences. Now, the Bohr model had shells numbered, 1, 2, 3, 4, 5, 6, 7, and the principal quantum number kind of follows the same rules. So n equals 1 would be the first shell, the one closest to the nucleus. N equals 2 would be a little further away, and so forth. So the lower the shell number, the closer the electron is to the nucleus, and the lower its energy. Basically, the way it works is the further the electron is away from the nucleus, the higher the energy. Now, there's some exceptions to that, but that's the general rule. So the principal quantum number is essentially all Bohr had. Now let's talk about the second quantum number, the angular momentum quantum number. Now that's abbreviated with a lowercase l, and I just wrote it in cursive there because the lowercase l in this font otherwise looks kind of like the letter I. But the angular momentum quantum number L is usually referred to as the subshell. So the principal quantum number is the shell, the angular momentum quantum number is the subshell. Now the subshell is interesting. It represents the shape of the region of space where the electron is. So in the Bohr model, the only thing you had were circular orbits. So essentially Bohr assumed all the electrons traveled in a nice, neat circular path around the nucleus. Now in quantum mechanics, we don't generally talk about path at all that much. So remember, quantum mechanics is a probability distribution. It says where is the electron likely to be. The angular momentum quantum number describes the shape of that space. And some of them will look kind of like paths, but you got to remember in quantum mechanics, we're modeling wave behaviors. So these subshells are more like the interference patterns you get when different waves interact with each other. So if you look at waves interacting on a pond, if you look at one wave coming from one direction and one wave coming from another direction, and when they hit each other, they build up in some spots and they go down in some spots. That's the kind of pattern that we see with these subshells. Now, L, the angular momentum quantum number, also contributes energy. So basically the energy of an electron is defined by the first two quantum numbers. Some of it comes from how far it is from the nucleus. Some of it comes from the shape of the region of space where the electron is found. So essentially we have distance and shape. Now we got two more quantum numbers to deal with. The third, before we do, let me show you some of those shapes. The angular momentum quantum number depends on the shell. So the bigger the shell is, the further it is away from the nucleus, the more subshells it can have. And these subshells are numbered anywhere from 0 to n-1. So in shell n equals 1, there's only one possible subshell, L equals 0. In n equals 2, there's two possible subshells. In n equals 3, there are three possible subshells, and so forth. Now, each subshell has a different shape, and I've crudely drawn a few of them here, and I will show you some nice, better drawings of them in a minute. L equals 0 is a spherical subshell. Now, that looks an awful lot like Bohr's circular orbits. That's not a coincidence. But as the shell gets larger and electrons start to interfere with each other, you start getting different patterns. So L equals 1 is kind of dumbbell shaped. Now, what I don't want you to see is I don't want you to see this as a figure 8, basically just the electrons zooming around in this figure 8 pattern. Basically, this is just two lobes that have a node or an empty space near the nucleus. So the electron is somewhere within these two lobes. N equals 3 has an L equals 0, an L equals 1, and an L equals 2 subshell. Now this one is kind of flower shaped. And again, this is not the electron just cutting donuts here in a parking lot. This is four lobes where the electron can possibly be. Now, it's kind of awkward saying n equals 1, L equals 0, n equals 2, L equals 0, or L equals 1. So, to make it a little bit easier when writing things down, they use a letter notation often for the subshell. So this first one here, this L equals 0, is called an S subshell. The L equals 1 is referred to as a P. The L equals 2 is referred to as a D subshell. And L equals 3 is referred to as an F subshell. So you might wonder why the first four are S, P, D, and F, and the rest of them follow the alphabet. Well, you might think that S stands for spherical. It really doesn't. It actually stands for a term from spectroscopy, which is what they use to analyze some of this stuff. It actually stands for singlet. You don't have to worry about that. Just remember the first four shells are SPD, or first four subshells are SPD and F. Now, the rest of them, following L equals 4 down, go G, H, I, J, and so forth. Now, I'll go ahead and tell you a little secret. Most of the time, we are only dealing with SPD and F, because we don't have any elements on the periodic table that, at least in the ground state, have any electrons in a G subshell. So it's these four that you should be familiar with. Now, if you want better renditions of what these subshells look like than what I can draw with my horrible drawing skills, then pull open OpenStax and look on page 305, and you'll see nice three-dimensional renderings of what these subshells look like. So the S subshell looks nice and spherical there. Here are the P's. You see the two lobes for each P? Now, we'll talk about the three different ones here. That's actually the third quantum number. But take a look at the D subshells. They look kind of flower-shaped, although there's an oddball one with a ring here. The F subshells, you'll see why I did not attempt to draw them on my screen, because I can't draw this kind of thing and have it look like anything that has any meaning whatsoever. One thing you'll notice, though, is that as you go from S to P to D to F, the subshells get more and more complicated. Now, in addition to looking more complicated, the higher order subshells actually have higher energies. So the energy of the electron goes up when it's in these higher order subshells. Now, if you're looking for this in OpenStax, it's on page 305. So you can find that in the book if you'd like to take a look at it on your own. But I just wanted to show you kind of nicer renditions of the shapes that I'm capable of drawing. So we've said that L indicates shape, and it also indicates energy. The third quantum number indicates orientation. Now, the way it works is the value of the third quantum number depends on the value of the second one. So if you have an L equals 0 shell, then there's only one possible subshell. Negative L to positive L would be negative 0 to 0, or just 0. Now, what that means is if you're trying to orient a sphere around the nucleus, there's only one way to do it, which kind of makes sense. If you turn a sphere, it's still covering exactly the same spot it was covering before. When the shapes start getting more complicated, though, you can have different orientations. As you saw in that picture from OpenStax, they actually do three different looking P subshells. They drew one like this that was facing horizontal. They had one vertical, and they had one kind of going in and out. Now, if you look at L equals 1 and follow this little formula up here, there's only three possible values for ML, negative 1, 0, and 1. Each one of these is one of these orientations. Now, I'll go ahead and tell you, it doesn't much matter, at least from our perspective, which number is which. It just matters that there are three of them. So there are three possible orientations of a P subshell. Now, why is this important? It's important because every one of these orientations, this one, and this one, you can see cover a different space around the atom. And each one of those can contain electrons. So each one of these orientations can actually contain electrons. And as you notice, the more complicated the shell is, the more possible orientations it has. And you can see that on page 305 in OpenStax if you pull out your book and go to that page that we were just on. Now, the interesting thing about these is that all of them have the same energy. It doesn't matter which one of the orientations you have, electrons in them have the same energy as all the other orientations. So it doesn't matter whether your electron is in px, py, or pz, it has the same energy as the ones in the other orientations. Now, so we've got 3 quantum numbers. The first 3 quantum numbers together describe something called an orbital. So the first quantum number describes distance, the second one shape, and the third which orientation you have. The 3 of those together describe a place where an electron can be, and we call that an orbital. It's kind of similar to the word orbit, but different because there's no path associated with it, so I guess they chose a word that sounded kind of similar to orbit, but wasn't quite. So I guess a question you would have at this point is, well, how many electrons can you stuff into one of these orbitals? And the answer to that is where the 4th quantum number comes into play. The 4th quantum number is called the magnetic spin quantum number, or just the spin quantum number. It's abbreviated MS. The previous one was ML. And unlike the other 3, or excuse me, unlike 2 of the other 3, this quantum number doesn't depend on which subshell you're in or not. Basically, this quantum number has 2 possible values. We call them spin down, -1/2, or spin up, +1/2. You may wonder about the 1/2 business. Well, these are the solutions to a mathematical equation. So that's where the numbers would come from. Now, what that means is that basically each one of those regions we were talking about, each one of those orbitals, can hold 2 electrons. One of them spin up, one of them spin down. Now, at this point, all of these little rules for quantum number values, n can be an integer, L can be 0 to n-1, ML can be -L to L, and so forth. Well, all those seem kind of complicated, and if you actually had to write down all 4 quantum numbers for all the electrons in an atom, you actually could do it. It would be incredibly tedious, but it's certainly doable. All you got to do is just write out all the possibilities. But it is kind of cumbersome, and it's not very informative if you're just looking at a list of a bunch of quantum numbers. So, one way to kind of get some order out of this chaos is to use something called an orbital diagram, which is basically just a nice map or a graphical representation of the quantum numbers of electrons. And essentially what it does is it gives you a nice map of the electron clouds. And once you have that, you can start actually making some kind of sense of what atoms are actually doing when they react. So below here I've got a sample energy diagram. It goes from the first shell up to part of the 4th. And the nice thing about these is that they're the same for each atom. So all atoms have the same ordering of these orbitals, and the difference is essentially how many electrons go into do you have, how far up the diagram will you go. Now, this would go on past 4p, but we're not going to worry about that right now. So, if you look at it, there's one thing about this diagram that you need to be aware of. These orbitals are not organized by place, so it's not really a true map, as in a map you would use to get to the store, but it's an energy map. And you might wonder, well, why did they use energy instead of distance? Well, the reason they use energy is that by and large, electrons arrange themselves around an atom by energy. So, and remember, distance is only part of that. So, what happens is each one of these orbitals down here at the bottom, the low energy ones, fills up first, and essentially you go up this chart until you run out of electrons. So, a couple things about the chart. Each blank represents an orbital, in other words, N, L, and ML, and each one of those can hold two electrons. Generally what we do with these blanks is we draw arrows in them, and we draw an arrow pointing up and an arrow pointing down. So one electron would spin up, one would spin down. One thing you might have noticed pretty quickly is if you follow the quantum number rules, 1s is first shell, s subshell. So this is N and L. Each one of these labels here is a value of N and a value of L. That's one reason it's nice and convenient to use letter notation rather than having 2 numbers sitting there. Each blank represents an orbital. the number of blanks is going to equal the number of orientations. So essentially the number of blanks is going to equal the number of values of L you can have. So in S subshell, you'll notice every one of the S's has one blank. The P subshells, every one of them has 3 blanks because there are 3 orbitals in each P. The D's, every one has 5, and so forth. Now, we're going to show some filled up ones in just a second, but one thing I will put here is when there's more than one orbital with the same energy, electrons generally don't pair up until each one has 1 electron in it. That's something called Hund's rule, which we'll discuss in just a minute. But all you got to know here is how many electrons there are, and then you just start putting them in from the bottom, working your way up to the top. One thing you probably did notice, though, is I've got a couple highlighted in red here, the 4s subshell. You might wonder, okay, the order of N would be 1, 2, 3, 4. The order of L would be S, P, D, F, and so forth. And you say, okay, it basically follows that order on the bottom here. But once we get past 3P, you might notice the next subshell actually in this chart is 4S and not 3D. And you might wonder why. Why don't all the 3s fill up before all the 4s start filling up? The answer is that the D subshell is really high energy. If you look at the diagrams from OpenStax, you'll see those shapes are really complicated. The more complicated the shape, the higher the energy. So the way it works out is 4s is actually a little bit lower in energy than 3D. So 4s fills first. And as you go further up in the orbital diagram, you'll see that basically every time a P fills, the next thing that fills is another S. And then a D will fill after that. Now, you're thinking, well, wait a minute, now I got to memorize all that stuff? Well, I will show you a way to get this ordering from the periodic table. But for now, just don't worry about it. Just realize that this is caused by the fact that both the principal quantum number N and the angular momentum quantum number L both contribute energy to the electron. So let's look at one of these with some electrons actually in it. Here is potassium. Potassium, symbol K, atomic number 19. In case you're wondering about the Z, a lot of times we just abbreviate the atomic number with Z. So if you see Z equals 19, they're just talking about the atomic number. Now, what I did here is I started at the bottom. I put an arrow pointing up, an arrow pointing down. I draw half arrows here because when I'm handwriting them out, drawing double-headed arrows makes it look worse. But in print, you'll see sometimes half arrows or double-headed arrows. Doesn't really make a difference. So I started off here. I drew the next ones here. Then I drew these. So I've used 2, 4, 6, 8, 10 electrons. Here's 12. Here's 14, 16, 18. And the last electron goes right here in 4s. Now, if you remember what we know about potassium, we know that potassium's a metal. And if you look in the periodic table and use the rules of thumb we learned in the earlier part of the course, if I said, what charge would a potassium ion take? Well, you would look and you'd say, well, potassium ion is atomic number 19. Nearest noble gas is back one at 18, so we'd expect potassium to lose 1 electron and form an ion with a charge of positive 1. Well, take a look over here. That last electron that's in the 4th shell, there's one in there. Would it surprise you to learn that that's the one that gets lost to form the potassium ion? Well, probably not at this point. And that leads to an important point. We said before that chemistry was all about the electrons. Well, for the most part, chemistry is all about the electrons, but it's about the electrons that are furthest from the nucleus in the atom. We have a special name for those electrons. The ones on the outermost shell of an atom are called valence electrons. If you're looking for the electrons that are involved in a typical chemical bond, those are the valence electrons. So, this electron all off by its lonesome in the 4th shell, notice that nobody else is there. There's no other electrons in the 4th shell, just that one single electron in 4s. Those are the electrons that will either be gained or lost in a chemical reaction most of the time. So the reason it's important to be able to figure out where the electrons are in one of these diagrams is because the ones in the outer shell are going to be the important ones. And you can predict a lot about the way a chemical is going to behave, or at least an element, by looking at how many electrons it has in its outer shell. That's going to dictate what kind of bonds it can form. That's going to dictate the chemical formula of the product you get when you react it with something. So the atoms tend to gain or lose electrons in the valence shell, in the outermost shell. These other electrons, these electrons in this core here, we call these core electrons, usually don't get involved in the bonding. In fact, the further you are from the outside of the atom, the less likely you are to get involved in chemical bonds. Now, I'll go ahead and tell you something about what kind of things the outer shell tends to do. We observe, and we'll explain why this is a little bit later, we observe that atoms seem to prefer filled or half-filled subshells if they can get it. They prefer filled, but for particularly the larger shells, the larger subshells that will contain a lot of electrons, they will sometimes be satisfied with a half-full subshell if it's a large one. So if potassium loses this one electron on the outside, what's it left with? Well, it's left with all of these subshells that are completely full. So potassium apparently is satisfied with that. So if you know how the electrons are arranged around an atom, you can predict something about the atom's chemistry. Now, talking about filling up one of these diagrams. I mentioned something before called Hund's rule. Hund's rule basically says that when you have two or more orbitals with the same energy, electrons will go into each equivalent orbital before pairing. So in other words, if you have a p subshell that has 3 orbitals in it, and you've got 2 electrons that need to go in there, the first electron will go in one of the orbitals, the second electron will go in a different one. Because they're all the same energy, they would rather take separate orbitals than pair. If you think about this, this should make some sort of sense, because electrons are negatively charged, they would naturally tend to repel each other a bit. So you would think an electron having a choice of 2 orbitals with the same energy, it would go for the empty one rather than one with an electron already in it. And that's in fact what we observe. So we fill up orbitals one at a time, as long as they're at the same level, same energy, until they all have 1 electron in them, and then you start pairing. Now, this is a little surprising, but there actually is experimental evidence to support this idea. So there's a property of an atom called paramagnetism. Paramagnetism is the attraction of an atom to a magnetic field. It's not quite the same thing as your refrigerator magnetism, but it's a bit related. But this paramagnetism basically has to do with the fact that electrons that are spinning carry a magnetic field. You spin an electric charge, you will generate a magnetic field. Well, if the if the atom actually has electrons spinning in one direction, electrons spinning in the other direction, and has the same number, then those magnetic fields that are generated will cancel each other out because they'll be opposite in direction. But if you have some electrons by themselves that don't have a counter electron here spinning in the opposite direction, then you will have an overall slight magnetic field, and that atom will be attracted or repelled to a magnetic field. And you can test this. So if you have the right hardware, you can test this fairly easily. And what we find is if we draw the electron configuration of an element, we fill in all the electrons in an orbital diagram, and you have only paired electrons, the atom will not be paramagnetic. But if there are some that are unpaired, the atom will be paramagnetic and will interact with a magnetic field. So this seems to be just kind of a little nitpicky point here, but it actually does have measurable, physical, real-world implications. Now, let's look at one more example before we close out this video. So let's look at something about transition metals. Now, transition metals we know can often form essentially more than one type of ion, and I've decided to use titanium for this example here. Titanium, atomic number 22. So we're going to fill 22 electrons into our diagram. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and here's 21 and 22. So notice these two are going in by themselves. They won't start to pair in 3D until we've actually filled all the blanks with at least one electron. Now, the thing I want to point out here is that titanium usually forms one of two ions. The most common charges of titanium are +2 and +4. Well, if titanium loses only the outer shell electrons, now actually these are the valence electrons right here, because remember what valence means, outer shell. These are the electrons in the fourth shell. These 3D electrons are higher in energy, but they're actually closer to the nucleus, because distance is given by n, the 3 in this case. So if titanium loses only its valence electrons, then it will form an ion with a charge of +2. But if titanium loses those valence electrons, it still has these high energy d electrons that are basically just hanging out there by themselves. So sometimes the transition metals will play a little bit with some of their inner shells as well. And if titanium loses both the valence electrons and these two, that's where you get your +4 charge. So you can kind of start to understand the different charges transition metals can take if you basically look at their outer electrons and look at the d subshell that's right underneath. So this is where all these different charges come from. Now, you're not responsible for trying to predict all the charges of all the transition metals, but I just wanted to show you that if you want to start to understand that stuff, you got to look at the electron configurations. You got to see where those electrons are, and that will tell you about the possibilities for transition metals. Now, of course, one thing you'll notice pretty quickly if you look at all the possible charges for transition elements, an awful lot of them have +2 as one of the possible charges. The reason for that is that most transition metals have an outer shell that has 2 electrons in it. So +2 ends up being one of the charges. Now, what we'll do in our next video is we'll talk about kind of shortening this a bit, because the more electrons you get, the taller this diagram gets. And it turns out there's a short form of the diagram you can use, which is usually referred to as an electron configuration, that will let you basically save a whole lot of paper. And we'll talk about that in the next video. But for now, that's all for this one. Thank you for watching.